Okay, so let's start today's seminar. Today we have breaking news given by Enric Pallé. I don't know whether you know, yesterday Enric and some collaborators from the IC have published a paper in Nature, and this is the resulting breaking news seminar of that publication. So Enric is a Ramón y Cajal Fellow here at the IC. I think Enric is in his second year of the Ramón y Cajal program. And, well, from my point of view, he's doing a very good work. So thank you very much, Enric, for giving this breaking news in a very timely moment.
Okay, thank you, Maria Rosa, because you can see that Maria Rosa, together with Pilar and Rafa and Eduardo, also did this work with me. And I include also Antonio García Muñoz, which is a new postdoc that we have here. That was not included because he came too late. We already had the paper out. But he's doing some work on modeling the result I'm going to show today, and he's already integrated into our little team. So I'm going to talk about the Earth transmission spectra that we obtained from observing at the moon when there was an eclipse. And it's what we call the pale red dot, as opposed to the famous description of our planet as seen from a far distance, the pale blue dot, which is a blue dot planet. When you observe it in transmission, it turns out to be a red planet. So let me introduce you to the problem. Today we have a very vast set of satellites and measurements and ground stations, and we know a lot of things about our planet. We can routinely monitor the extent of the ice on the Arctic, plankton blooms, city lights. We can know if somebody's grandmother in Moscow had the light on that day and wasn't home. But when we go to an astronomical distance and we ask ourselves, how are we going to see extrasolar planets, we need to put ourselves in the position of E.T. looking at far away and see how E.T. would look at us from a really far distance. And how would E.T. look at us? Well, if we are to find an extrasolar planet, the thing we will need to do is actually see this little dot. And this is a very nice picture of Saturn and its rings. And it makes a natural coronagraph because if you amplify this little region here, you see a little dot. And this is from, I think it's the Cassini spacecraft around Saturn. So this tiny dot is the Earth. And we are still inside the solar system. So you can see that when we observe an extrasolar planet, there will be a little dot of light out there. And we will have to measure the photometric and spectroscopic properties of this little dot of light. And from these macro-scale properties, we will need to infer what this world is made of and what are their characteristics and whether life can harbor in that planet. So there are three ways. I'm going to make you a little introduction so you can understand where our paper sits. There are basically three ways in which you can observe the Earth as a planet, losing the spatial resolution. The first one is you build whatever instrument you want and you fly it really far away as the Cassini did. But we normally don't do that. We have very few observations. They make a very nice photo opportunity for many of the missions that go out there to the other planets. But the Earth is not routinely observed from remote platforms. The second way in which you could do that is to make a compilation of these high spectral and high temporal and high geographical resolution data that we have from Earth-observing satellites and try to composite together a global picture. But in order to do that, you need to use some models because all these little images are taken at different times, different days, etc., etc. And there's a third way that Pilar and I have been involved in doing this for a long time, which is to do Earthshine observations. You see the light bouncing off from Earth being reflected on the dark side of the moon. And I'm going to introduce this very briefly because we will compare it then to the observations that I will show. What is the Earthshine? Well, basically, the sun puts light in all directions, illuminating the day side of the Earth and the day side of the moon. But if you are to look at the dark side of the moon, it's also bright, especially if the crescent is thin, you can see it with your own eyes. And that's because light from the Earth is reflected in all directions and illuminates the dark side of the moon. So if you take the ratio between the brightness on the bright side and the dark side of the moon, you get the Earth albedo. And if you do it with a spectrograph, you get the reflected albedo of the Earth. And this was explained already. It's not in extra pH, but it was explained 500 years ago by Leonardo da Vinci. he already got it right that the dark side of the moon was illuminated by the Earth. At that time, he thought that mostly it was because of the oceans reflected a lot of light from Earth. And this is not true, because actually the oceans are among the darkest surfaces on the Earth. And he also thought that the moon was covered in water. That's what we call the mare. And that's why it was reflecting light back. But anyway, the geometry, he got it right already. And Pilar has several papers related to this, in which we obtain the reflection spectra of the Earth. This is how the Earth looked like if you were to observe it as a point. Would be the globally integrated spectra of the Earth. And it shows all the signs that we know of our atmosphere, and some signs of life, like the Rayleigh scattering, the ozone bands, oxygen bands, and water vapor bands. And this is a paper from 2006, which covers the visible wavelength. Now we have extended this into the infrared in order to compare with our transmission data, and I will show it later on. But basically, this is the way in which we obtain the spectra of a planet, in this case the Earth, the reflected spectrum. It means the light, the sunlight that would be bounced off the planet. But when we go out there and we try to isolate the light from a planet, this is very tricky to do. In fact, it's so challenging to do that we don't have the means to do that. If we were to discover an Earth-like planet around a solar star, or even smaller, an M star, we would not have the technical means yet to isolate the light using coronagraphy or interferometry. We have plans to do it, but it's not clear how long it will take us to get there. But the atmospheric characterization of the hot Jupiters has already been accomplished through a way which is can be achieved doing transit spectroscopy. It means that not all the planets transit, but if you have a planet that does transit, which means it passes in front of the disk of the star, you can take measurements of that star when the planet is not in front of it, and then you can take measurements of the star when the planet is in front of it, and if you do the ratio, what you get is the signature of the sunlight or the starlight that is able to pass through the atmosphere around that planet and reaches you and has a signature and information for all the molecules and the main components of the planet atmosphere. So what about transiting Earth? We will be able to do that. Maybe we'll be able to do that in the near future. But our idea was, what are we going to look for? How does Earth look like in transit? That would be the first thing to do, to know what the only planet we know harbors life looks like in transit. And nobody had done it, because you have to go far away and wait for the sun to transit, or you can do models, and there were several models being published, so we thought we knew how it looked like, but there were no observations. But it turns out that actually you can do that using something similar to what we use on the ocean. On the ocean, we use observations of the moon, say, in a normal day, where there's a crescent. But during a lunar eclipse, what happens is that the moon goes through the Earth's umbra. When it is in the umbra, no sunlight, no direct sunlight is able to reach the moon because it's eclipsed. But the moon is still illuminated. If you've ever seen an eclipse, you will see this orange-red light being illuminated in the moon. And this is light that has gone through a ring of the atmosphere. The moon would be sitting here, right? The sun is far away. No direct sunlight can reach the moon, but if you were sitting in the moon, you would see a ring of atmosphere around the Earth. This is very exaggerated. And some of this light would pass through, bend a bit, reach the moon, and go back to an observer on the night side. And that's exactly what we observed. We observed the spectra of the moon when there was an eclipse. And we did that using the NOT telescope and the visible from 0.4 to 1 micron, and the William Herschel. We were able to change filters quite quickly, and so we were able to cover the whole range from 0.9 to 2.5 microns. So effectively, we go from 0.4 to 2.5 microns. So this is an image taken, made by Pallé, by the way, in which if you were to sit at the South Pole, which was the deepest into the umbra, on August 16, 2008, this is exactly what the constellations would look like to you, and this is exactly what you would see. The Earth blocking the sun, you would not see this ring around here, all right, because this is made with the program stellarium, which considers an atmosphere. You will only see a small ring around the Earth. And I simulated this as close as I can, so if there was an eclipse and we had been able to go to the moon, Maria Rosa would be taking pictures of the eclipse, like she did there. So anyway, in order to correct for the telluric atmosphere in top of our telescope, and that's very tricky, because if we are to look at an Earth-like planet and the planet atmosphere is exactly like the Earth, because it's an Earth-like planet. So in front, between the planet and the telescope, we have our own atmosphere. So we have to get rid of our own atmosphere in order to make sure that the molecules that we are detecting do not belong to the local atmosphere, but to the planet. The same happens during the eclipse. So we actually took the umbra, the penumbra, and the bright moon. This is for the same region of the moon when it was, I think it's the South Pole, when it was within the umbra, within the penumbra, and within the bright moon. And you can already see that some features like this one here, I'll explain later what this is. This is the ZJ band from LIDIS. It's present in the umbra, but it's not in the penumbra or the bright moon. So what we can do is now divide the umbra by the bright moon, because the umbra contains the signature of the solar spectrum. It also contains the signature of the local telluric atmosphere and the bouncing of the moon. Although it doesn't introduce any band, it does have a wavelength dependence. But it is also contained in the bright moon. What it is contained in the umbra but not in the bright moon is the passage through this ring of atmosphere. So if we do the ratio between the two, we can isolate the transmission spectrum of the Earth. And this is, to convince you, this is the H, I'm sorry, it's not very clear. This is the H-alpha line. If you look at the umbra spectrum, which goes this way, you can see the H-alpha line marked because it contains the solar spectra. If you see the bright side of the moon, it also contains the solar line because it also has the solar spectra. But when you do the ratio, only the features that are related to this ring of atmosphere around the Earth are preserved. And there's no H-alpha on the Earth, so the ratio, which is a dark line, has no H-alpha. And so it happens with all the solar lines and all the features that we see on the Sun that we don't see on the Earth. So anyway, if we do the ratio over the whole spectrum, we calibrate it to have the whole spectra from 0.3, 0.4 to 2.5 microns. This is how the Earth transmission spectra look like. And there's a rich variety of things inside here. I will go in detail now. But basically, you see that the Earth will look much brighter towards redder wavelength than it is in the visible, where almost all the light is scavenged by the Rayleigh effect. The same thing that makes our planet blue in reflected light, it makes it red in transmission. So now I'm going to show you plots. This is very high resolution. It has a signal to noise about 1,000 or 800 to 1,000 along the spectra. And I'm going to show it in pieces because most of the information is lost when we put it together in this large spectrum. So if we start in the visible, this is the spectra from NOT. You can already see that there are several features. Water bands, of course. We detect water on Earth. There's also marked oxygen bands, 1, 2, 3. Oxygen alpha, oxygen beta, and I don't remember which one is 2, and gamma, I think. There's also the signature of oxygen 3, ozone, because if you were to apply a wavelength, a Rayleigh scattering dependence, it wouldn't actually go this way. It would actually go somewhere this way, right? So all this dip here is caused by ozone, a large Chapuis band, very broad absorption feature. But we also see calcium 2 down here, and especially marked the triplet at around 0.85 roughly microns. And this is a signature of the Earth ionosphere. This comes from the higher layers of the atmosphere. And that was a surprise to see. So we actually can say that we detected the ionosphere of the Earth. If we do a zoom of this area, and I divide it in two, so that you can see this flat area here, you can also you can see the calcium doublet, and maybe some signatures of NO2. We're not sure. We will need to fit some models into this spectra. Maybe it's too noisy to see it. And you can also see it here, a double dip. This is O4. This is a dimmer. This is O2, O2. These are van der Waals molecules. And I'll talk a little bit more about this because they are more clear in the near-infrared range. And all these things here, you see that our spectra is actually very smooth and almost no signal to noise until actually you go 5,500 nanometers, 5,500 angstroms more or less, and then you get all this noise, which we didn't understand at the beginning. Now we know what it is. It's the Fraunhofer line structure from the sun caused by the atmosphere. And it's actually not noise at all. It's a structure that we understand now. But the noise level, you should see it here, is very smaller. And there's a lot to explore here, but we haven't done much around here. If you look a little bit more towards the end of the visible, you see the H alpha should be here. You see it's completely removed. It's a solid line. And the calcium triplet is already here. So now we move from the visible in the knot, and we go to the ZJ band on the Lyris, on the first of the Lyris bands. And what we see is that we have CO2 band, small CO2 band, of course, really deep absorptions from water in the atmosphere. And we also have oxygen line around here, an oxygen band. But this band is not made only of oxygen, it's also made of dimers. Dimers are van der Waals molecules. I'll explain what it is now. But basically, these are loosely bound molecules in which two molecules of oxygen 2 bound together and have some deep, broad absorption feature. And the same happens with O2 and N2. So since we have, and here, this feature here, which doesn't appear in any other spectra that has, or any model, is the feature of O2, O2. These are called dimers, right? So what does this tell us about the Earth? Well, 78% of the Earth in volume, of the Earth atmosphere, is nitrogen, and it doesn't have any feature. So if we were to look at the spectra of the Earth, we would have to work really hard in our models to understand that there is nitrogen in the atmosphere, because it has no signature. But actually, through the interaction of these dimers, N2 and N2, if we had this spectra and a good model for an extrasolar planet, we would have isolated bands of oxygen 2 in the visible, so we would know how much oxygen 2 there is. We could fit then this feature here with O2, O2, and then we would have a remaining, if we had done our modeling well, there would be an unmatch between our model and the observations around here, which would belong to the interaction between O2 and N2, and then we could have a first-order estimate of how much nitrogen there is in the Earth's atmosphere. And that's the first time somebody, I think, devised a way in which I have a first guess of how to measure nitrogen on a rocky planet atmosphere. And that's a few words about atmospheric dimers. Well, they're not very well known. They are not in the, these are van der Waals, I already explained this, they are van der Waals molecules, weakly bound. They are minor rather than trace species in the atmosphere. It means that they are not very abundant, but they are not rare at all, and cause very broad absorption continuums. And they've been observed on Earth, as I show you, also in Jupiter, in the farther infrared, and in Ganymede, Europa, and Callisto as condensates. And all the work that we know about this has mainly been done in the laboratory, trying to understand the line strength of these creatures. But there's lot of its physics remain unknown, and actually these observations and more high-resolution observations of eclipse can actually help us to understand these molecules. They have been never observed in Venus or Mars, but Antonio assures me that the literature says that they should be there at the lower layers where we cannot see them, and mainly will come from CO2, probably CO2 dimers. And they are not contained, at least completely, in the most common spectral libraries that people use to do models of atmospheres. Now we go to the last range in the HK band, also from Lyris, and what we see is more marked features of CO2, very clear now, more water vapor, but very importantly, a very strong band of methane. Methane has a very strong diogenic origin on Earth, and we thought it would be there, but it was surprising to see that such a small gas, it's a trace amount in the atmosphere, it's really 1 part per million, a few parts per million, and actually has a very clear signature in the spectrum. And that's very interesting because it means that it may be easier to detect on an extrasolar planet than we previously thought. There were models. I'm showing here a model from Kaltenegger and Trapp, which is actually on the Astrofísica. It's not published yet. But there were other models. Ehrenreich et al. And colleagues have done other models. And I have stretched this figure so that it looks more or less like our figure. And you can see that there are several differences. If you look at the blue lines, these are water vapor bands. So you can see that it's very dim, the presence of water vapor in the atmosphere. But a fair comparison would need to be done in grid scaling things. But but you can see how deep our absorption is, almost to zero, right, on the water bands, and it's very weak compared in the spectrum. The green line would be these streamers. They are not contained on spectral libraries, so they're not modeled. They're not here, but actually it's very deep, this feature. I go backwards. You see that it's actually a really sound feature. And also the methane, which is very poor here, or very weakly shown up here, is very deep, actually. It's unmistakable here. And there's some water past 2.3 microns, but this depth here is no mistake, it's methane. Right? And you can see how the strength of the CO2 bands compared to water is different. We have our bands of CO2 here, and water is actually more strongly absorbing than CO2. So actually, there's a lot to improve in the models. And the big question is, how deep do we see into the atmosphere? Because the light will pass through an atmosphere, and how much is the light is able to penetrate depend on the wavelengths also, but it will depend on the height. If you go higher in the atmosphere, your path is shorter, so more light will go through. If you try to probe the layers close to the boundary, to the surface, the rocky core of the planet, then you have to cross through a large part of the atmosphere. Most of us are astronomers, and we don't observe at air mass more than 4 or 5. Well, this air mass could be, the average air mass of our atmospheric spectrum could be somewhere between 70 and 90. So it's a lot of atmosphere that we're crossing through. And that's why the dimmers show up and don't show up on a normal telluric spectra, because the number of molecules is very different. So determining the minimum altitude that we are sampling in our data is very tricky because of clouds. We could have patch clouds. If we have a thick cover of clouds, we will see it, but we don't know what clouds look like. And if you look at the planet, I'm sure there will be locations with clouds and locations without clouds. The clouds to you look sideways, so if they only extend for a few kilometers, you may be able to look through them on the bottom. If they extend for thousands of kilometers, they will block the light. So we don't know. We have no idea, but we are hoping to get a rough idea. We believe that because of the depth of the features that we see in our spectra, we're actually sampling to the very lower few kilometers of the atmosphere. But that's a guess right now. And we want to determine the minimum altitude, and we're going to try to do that through modeling, through fitting models to our spectra. And the lower, knowing the minimum altitude is interesting because some anthropogenic signatures, some very low gases which are man-made, may be down here, and maybe, I'm guessing, I put an inversion. Maybe we could detect them, and maybe there's a signal from the surface. But I regard these as very unlikely. It would have to be a glancing angle. But sometimes, maybe, if there's an ocean, it has this glint scattering. I think the angle would prevent it from doing it because it should be almost 180 degrees. But it would be nice to know how this minimum altitude. And this is just a graphic that shows the abundance, the column number density of these dimers as a function of altitude. And you can see that you can contain almost 99% of all dimers in the atmosphere in the bottom 5-10 kilometers of the atmosphere. So that's pointing, that's a small lead towards telling us that we're actually sampling lower than we thought, or that was thought in the atmosphere. And also, I showed what the average spectra looks like, but we were able to take several spectra, quite a lot of spectra during the eclipse, so we can see the evolution, the temporal evolution, as the moon goes in and out of eclipse of these bands. And we're hoping that the model, not only to the average spectra, but to all these individual spectra, will tell us something about the composition and the structure of the atmosphere and how deep we are sampling. So I'm going to now try to compare what our results imply in the search for extrasolar planets. We have two methods: reflection versus transmission. Reflection would be try to block the light of the star and directly get the light from the planet around it, versus transmission, try to characterize the atmosphere of that planet through transit. And I'm going to talk only about characterizing the atmospheres and finding life on them. To do that, you remember I told you about these Earthshine spectra that we normally take for other reasons. We were able to take the Earth's reflectance spectrum through Earthshine observations with the same instrumentation that we use for the eclipse. So we also cover from about 0.4 to 2.5 microns. This little part here in the visible, we were not able to have the knot, so we we added it from a different day at different times than the infrared. But basically, it's the first guess of what the reflection spectra look like. And then we can compare them. We can compare the information that we would retrieve if we were to observe the Earth, the direct light that is reflected from Earth using Earth-chain observations as a proxy, and the light that we would obtain from a transiting Earth using the eclipse as a proxy. And you can see the blue one would be the reflected spectra, and the black one would be the transmission spectra. And the relative flux is actually a relative scale, so it doesn't mean you have more flux here in reflection than in transmission. The flux, actually, you always get almost all the time more flux on the transmission. And if you put all the different features, you can see that the blue planet is a red planet, but the oxygen features, this one is almost the same depth, but the dimmers are only present in the transmission. The oxygen, CO2, and methane bands become much stronger in the reflection, in the transmission than the reflection. Especially this methane here is missing in the reflecting spectra, while we can clearly see it on the transmission. Now, a table. There should never be tables in a talk, especially if they have more than 3 columns. So I don't want you to read this table. But what we did here is these are several molecules and these are several bands. Okay, and all we did here is calculate in the transmission spectra and reflection spectra a different signal to noises if we are able to retrieve with confidence these molecules. And you can see that if we have an infinite signal of noise, like our observations, or a signal to noise about 1,800, that was our observations, we retrieve all of them. But we don't retrieve all of them in the reflection spectra. When you lower your signal to noise by introducing artificial noise into our measurements, we see that at signal to noise 10, we lose some of the bands. At signal to noise 5, we lose a lot of bands. But we're still able to see 3 bands of oxygen, 1 band of O2 and N2, these dimmer bands, CO2 and methane. So even with a spectral to noise 5 instead of 800, as I showed you, in the transmission spectra we would see oxygen, CO2, methane, and dimmers. If you use the reflection spectra, the light reflected directly from the planet, you can still see most of the bands when you have a signal to noise about 800, like our observations. But when you degrade it, a signal to noise 10, you only can see water, basically, and some dimmer band. And if you have a signal to noise 5, which is more likely to what we will have on an exosolar planet, you don't see anything. So the conclusion is, if you want to characterize the atmospheric components of a planet, you better have the transmission spectra, or a very high signal to noise reflective spectra. So now comes the question. All these sometimes sounded like science fiction. How far away are we to technically doing this, these measurements and retrieve the planetary spectra, and what kind of instruments do we need for the future? In order to characterize these telluric planets, the first thing we need to do is find them. And if we build a large instrument like the James Webb or the ELT, GTC won't do for that. We won't dedicate these large instruments to finding these Earths, because this would be a large program. So we need the inputs, right? And the inputs are probably going to be provided by missions like CoRoT and Kepler. These are the ones that we have now. Maybe Plato, TESS, ground-based searches around M-stars. Maybe they can feed us also some small inputs. Find one of these rocky planets in the habitability zone of an M-star, or that would be really nice, because if it's a G-star, we are more far away in the future to look at that. But if you look at the goals that are published on the web for CoRoT, which is observing in the Cygnus region, it says that Kepler, is going to retrieve about 50 rocky planets in the inner orbits if most of the planets, or most of these planets, are the size and radius of the Earth. If they are a little bit larger, 1.3% the radius of the Earth, or 2 times the radius of the Earth, it could go to much more, hundreds of planets. Most of them will be around a G-star, in which we will have almost no chance to look at this transmission spectra. But it is possible statistically that 1, 2, 3, 4 may come out to be circling around, orbiting around M-stars. And if that happens, then is when we try to model how we did that. And now, since we have our transmission spectra of the Earth, we can use this. What we did is use the flux from the star, the the spectra from a star that we know, we have real measurements, and we can put and try to make the simulations to see how difficult it would be to detect these features. So what we do is we take the spectra of the star, and we take away the flux that is blocked by the planet, which is inside, which is transiting, and the flux of the planet area, the rocky part, and the ionosphere, right? But then we add this term, which is the ring of atmosphere around the planet multiplied by the transmission spectra, which I just showed you. We measured for a rocky planet, and we put it inside here. We add some noise, and then we divide everything by the stellar spectrum when the planet is not in, so it's just the plain spectrum, to which we add independent noise. And we do the ratio between the two, and if there was no noise added, then the retrieval would be exactly the transmission spectra of the Earth or the planet in this case. But actually, because we add noise, if you are to make one measurement of one spectra signal to noise 1,000 outside transit and inside transit, what you have is when you do the ratio, the green thing here is the spectra you should retrieve, and this is actually what you retrieve. So the noise is hundreds of times larger than the features in your spectra, and this large noise corresponds to bands in the stellar spectrum. It has nothing to do with the planet, and this is because when you have a absorption band in the star, you have less flux, so you have larger error, right? And this is for an M star and an Earth circling around an M star. But of course, we won't be able to do one transit. This is a 3-minute exposure, 1,000 signal to noise ratio done with the ELT, right? The extremely large telescope time calculator. But we won't be able to do it once. We will be able to do it several times. So we will need to start averaging transit measurements, pairs of measurements, inside and outside transits. So if you go back, and I should really tell you that this is work in progress because we still have to put a lot of things into our model, but our first order guess is that when you put together, you average 5 of these ratio spectra, the ratio spectra being the ratio between in and out of transit. When you average 5 of these spectra, you still see nothing. This is now the green here would be the transmission spectra of the Earth, and the black would be your actual measurement, so you see you're really far away. But when you start putting together like 100 spectra together, which would lead to an integration time of 5 hours, 10 hours for you, 5 into transit and 5 outside the transit, you start seeing some features. When you go to 25 hours of observation, it means 50 hours of integration time on target without overheads, then you can already retrieve the measured features on the Earth transition spectra, like methane, water vapor, oxygen, and so on. If we have someday in the future when the Earth is built, this, no mistake, we found life outside the solar planet. And still, some people would have listened to this talk and say, well, we should abandon completely looking for the direct light of the star and go to transmission. That's not really right. I think, with my humble opinion, is that the first characterization of an atmosphere, I don't know whether you find life or not, but the characterization of what the atmosphere of a rocky planet is made will come probably through transmission spectroscopy, because that's technically easier for us to do with the larger telescopes that we'll put out there in the next decade. But trying to isolate the light from the planet itself gives us a lot of indirect information that the transmission spectra cannot do, like everything which is related to the surface of the planet, like the presence of continents, getting the rotational period, try to see if there are some biomarkers, like the signs of vegetation that Pilar has found on Earth. But also you can look at the planet not only when it's transiting, but when it goes around, and you can see the orbital light curves, you can see the glints of oceans and look for polarization effects. All these things are a lot of additional information of the planet, so we should pursue both lines of research. I forgot something, but I don't know where it is. Anyway, I go to the conclusions, and the conclusions is that we have obtained the Earth's transmission spectra from 0.4 to 2.5 microns. As a first order, we are able to characterize almost all the components in the Earth atmosphere and detect all the biomarkers that there is to be seen. We also make a detection of the ionosphere through calcium-2, and But calcium-2 is not the more abundant ion in the ionosphere. If we had extend our observations a little bit farther into the blue, we probably would see magnesium, which is the more abundant one, and iron, but they were outside of wavelength range. We also detect dimers that may become very important in order to detect extrasolar planets. And one of the reasons is that in our simulations, what we see is that these features of dimers are actually present on the planet spectra because you're seeing intermission and go through a large atmosphere, but are not in the telluric corrections. So if you actually one day retrieve the spectra of an extrasolar planet from the ground, if you see that feature, then you are almost certain that the rest of the features you see are not your local telluric spectra, right? And our conclusions is actually if you want to characterize the atmosphere and find out whether there's life on that planet, the transmission spectra gives you much more information for that particular purpose than the reflectance spectra. And after that, I show you something which doesn't belong to this paper. It's published yet, so we're working on progress. But basically, using this transmission spectra and using real spectra of the stars, we do an exercise of building a sort of an empirical model of how good we need our measurements to detect that. We're using ELT, but we're planning to extend this to using James Webb, etc., and putting some real noise to the expected instrumentation and telluric absorption, etc., etc. But basically, we see that for an Earth, within the habitable zone of late-type M stars, it is possible to detect waters, oxygen, methane, and CO2, which means life, within a few tens of hours of observations. I put a nice picture that Danielle gave me to put on the press release, so thank you to all of you and Danielle. Thank you.
So there's time for questions, comments, questions.
These M-stars, they are pretty active objects and so on. Do you think the stability of the M-star spectrum compared to the level of detection you are looking at over a time scale of a few tens of hours will be whether the spectra will be stellar spectra stable enough to be able to detect the planetary signal in it?
That's one of the key issues. One of the key issues is the stability of the instrumentation that we're going to use, the level of activity of the star. We think this may have a less impact because the transits will be quick and we'll be able to measure just before and after, before and during the transit. So hopefully, will at least part of this activity go away when you do the ratio. And we plan to do the ratio individually, day to day, or transit to transit. But the stability of the instrument is very important. More important, I think, is also the variability of your telluric atmosphere from hour to hour and from day to day. And we are right now putting this into our simulation. That was out of the atmosphere. That was using a space instrument, right? With our first guess of the noise. Now we want to do it with a ground-based instrument, with putting real telluric, adding noise, which is adding a telluric spectra into our spectra, which varies every minute or so. So it's working for us. But if it's not feasible in the next generation of instruments, we will be on the second.
More questions?
I'm noticing the comparison that you've made of the features of your spectra with the simulation. There is something more to that, and it's that your spectrum is more red.
Yeah.
And the slope of the spectrum is better than the simulation. Why is that?
The slope of the spectrum, I think it has to. You mean, not the last part. You mean the simulations of the transmission that were published. I think that's due to the geometry and also how deep you're sampling into the atmosphere. If you're sampling deeper, your path is longer, so you're going through, you scavenge more blue light, and your red, the redness of the spectra would be more pronounced. I think to answer properly that, we need to model, and then know how they model the other spectra and compare them. But I think it has to do with geometry.
Well, mine is just a comment. The last equation you put in your conclusions is not right. I mean, carbon dioxide or methane are not life. So you
No, no,
really
no.
need amino acids.
I should have explained it.
And
better.
you really need different things.
This is what is called the triple fingerprint. If you detect water, it's not a biosignature. If you detect methane or CO2, it's not a biosignature. If you detect water and ozone or oxygen, that's a proxy of oxygen, and methane, or one of these three containing either methane or CO2, I mean water, oxygen, and one of these two, this means life. Because these three don't occur, they are not in equilibrium. If you had an atmosphere like this, it would vanish in a few thousand years. These are maintained through the biological cycle. There's no geological formation that can maintain these three elements in an atmosphere. Oxygen and CO2 and methane are continually produced by life. So there could be a presence of methane on an atmosphere. There could be a presence of CO2 in an atmosphere. But the simultaneous presence of oxygen in large proportions, right? Not trace amounts. The simultaneous presence of a large amount of oxygen, water, and CO2 or methane means life. I mean, that's quite accepted in the astrobiology. Not individually, but it's real.
More questions, comments, suggestions?
In some part of your talk, you talked about you didn't know what was the depth, the height about the Earth, the rocky part of the planet that you were looking through in your transmission spectrum, and you were going to derive that information from a model of Spectra. Could it be possible, just from images from the shuttle or whatever spaceship around the Earth, to just look on the images they take of the horizon from a height of hundreds of kilometers to estimate what is the transmission through those atmosphere, through that amount of atmosphere, and to infer how would be the transmission you would expect? Wouldn't it be a better approximation to that figure? Yeah.
In fact, that sort of goes back to the point that to construct a global view, you could use these measurements. But so in theory, yes. But when you go to the practice, it's more difficult because there are several instruments up there, they are called limb sounders. And what they do is, instead of looking at the Earth, they are in an orbit in which they are always seeing the sun set or rise to the Earth, so they go through a path and they make measurements. The problem is these are local measurements, right? Depends on how big this path is. They're not far away from the global mean, but they cannot see the whole planet at once. But also, if you want to measure atmospheric species in the atmosphere, you need a much higher resolution than what I show. I show a resolution of about 1,000. No, singleton is about 1,000. Resolution was about, I don't know, do you remember? Resolution, no, wave, no, resolution. Armstrongs. Yeah, 10 Armstrongs, more or less. Right? But if you want to measure atmospheric species with precision, as they vary with the seasons and so on, then you need a much higher spectral resolution. So these instruments are built for higher spectral resolution, but over a much shorter wavelength interval, right? So we were not able to see spectra that cover this wide wavelength interval from remote satellite platforms.
Just to estimate the amount of atmosphere what height can you look at that you're not blocked by the atmosphere? You don't need to have a spectrum. You just need to see whether you see light or not.
Wow.
So you just need to make I'm guessing.
But the height at which you sample depends on the wavelength. So
yeah, sure, but you don't need to have a spectrum.
If that were to work, you would know at that part of the spectrum how deep you sample. But the other thing is these satellites have a narrow field of view. So if they hit a cloud, there's no transmission. If they don't hit a cloud, they see the clean path. We are hitting clouds and clean paths mixed together. So if we had no clouds, I guess the models would be much better than they are.
If I understand correctly, you measure the Earth's reflection spectrum by looking at the new moon.
No. By looking at the moon when it's crescent, waning or working.
Yeah, when there is a crescent,
yes.
In the new moon. So the properties that then you measure a spectrum which is in some way contaminated by the reflectivity properties of the moon.
No, because we do relative measurements. So it's the same as during the spectrum. We do a relative measurement, right? So we measure the ratio between the spectrum on the dark side of the moon and the bright side of the moon. Yeah. So the bright side of the moon has the spectrum of the sun and the spectrum of the local atmosphere, because you have a telescope here and you pass through the atmosphere, right? The spectrum of the dark side has the solar spectrum, the spectrum on the reflections, the spectrum of the moon surface, and the local atmosphere. And the bright side also had the moon. So the stellar spectrum goes away, the lunar reflecting spectrum goes away, and the local telluric spectrum goes away. So you are only left with these reflections. We choose areas on the moon on the dark and bright side that are always the same and have the same, and they have the same properties. Yeah.
Okay. No more questions, comments? So Enric office is located in the second corridor, so you can contact him at any time. And let's thank Enric again for his presentation.